There are many different types of the decoders. I will not go into each of them, so you can just refer to your book. And basically the concept is always the same. For example, here you can see the BCD to 7-segment decoder. So in this case, you have the display, the 7-segment display, and it shows the different values depending on the input. So for example, if you want to show the 1 here, so let's say if you want to show the display the 1 using this 7-segment display, what you have to do is B, you have to go, the B have to be high. So let me change the size. So B have to be high, and C have to go high. So in this case, it will show the value of 1. Or for example, if you want to show the value of the 2, so in this case, A is to go high, B, the G, E, and then the D. So this is how you're going to show the output 2, right? Now, using this, you can actually create a truth table for this circuit. So I think there should be the truth table. Oh, okay, if it's not here, just look up the truth table in Google. You can just look up, and you can actually create the logic circuit for this 7-segment display. And this is you have the BCD, you have the 4 inputs, and based on this, you can generate a different output. Okay, so this is another useful tool that you can use, right? So you can use the different logic circuits to create or to use it with a 7-segment display. We have the encoders. Encoder is just the opposite of the decoder. So in this case, you have the decimal input, and it will generate the binary output. Okay, that's it. So this is just the opposite of the decoder. Again, you can actually create the decoder or the encoder just by looking at the truth table, right? So by using this truth table, you can create a functioning encoder. Okay, so this is one of the examples. Now I will not go into details of each circuit because there are too many circuits to cover, right? And we don't have enough time to cover all of the circuits. I'm just showing the slides. You can just refer to the slides, and you can actually try to create this circuit using the circuit verse and see the relation between the input and then the output. So this is the encoder. So for the BCD, so you have the 10 inputs. So just consider each input as a 1 decimal number. So decimal 1, decimal 2, decimal 3, etc. So for example, the input is 1. The output should be the 0001, right? And so on. Okay, so this is just one example. You have the code converters. You can convert from the one binary to another binary, right? So for example, in this case, they're converting from the BCD to the regular binary. Again, this is a truth table, and just using this truth table, you can create a logic circuit. We already cover how to do this, and you can try this on your own using the circuit verse. Okay, so this is just the example how it works. We have the multiplexer. So what is multiplexer? It can select the data, right? So this is the data selectors. The device allows the digital information from several sources to be routed into single line. So if you have the multiple inputs, so these multiple inputs can be transmitted through the single line. So this is like the parallel to serial conversion. So you have the parallel inputs, and that parallel inputs can be converted into the single serial output. So actually you can actually try this inside the circuit verse. So let me open the circuit verse. So this is multiplexer here, you can see, right? So what's happening is that we have the multiplexer with 2 inputs, input A0, A1, okay? And then we select which input will go through the output. So for example, this is the bit selector here. So let me change this, the bit selector. Okay, since we have only 2 bits, right? So A0 and the A1. So let's say if we want to select the A0, we just send the bit selector to be 0. So in this case, the 0 bit is selected. Bit 0 is selected. A0 is selected in this case. So as you can see, the A0 is selected and the output is equal to A0. If I change the bit selector to the 1, now the A1 is selected. So multiplexer, in this case, the multiplexer will send the A1 through the output. So by changing the input and output, I can change the sequence of which bit will go through the output, right? Okay, and this is the same implementation, but in this case we have the 4-bit input. So if you have the 4-bit input, then you have the 2-bit selector. Why? Because with 2-bit selectors you can select the 4 bits 0 0. If the input is 0 0, the A0 will be selected. So let me change this one. So the label is in this case the A0, right? So this is the A1, this is the A2, and this is the A3. Okay, so by changing, for example, when the input is the bit selector is 0 0, so this is a bit selector. So when the bit selector is, for example, the 0 0, A0 will be selected and A0 will go through the output. So in this case, A0 is equal to 1. If, for example, the input is 1 1, so if 1 1, then the A3 will be selected, right? So 1 1 is equal to the 3 binary, the decimal 3. So in this case, the A3 will be selected and this 0 will go through the output. So this is how the multiplexer device works. Okay. So this is just the symbol for the multiplexer. We have the 4 inputs and then you have the 2 data selectors, right? So bit selector or the data selector inputs. So this is a data selector. So let me change this, all right? So according to the book, so it says the not bit selector but data selector because we have the 2-bit input. In this case it's a bit selector, in this case it's a data selector, but the same. And this is the output. So that depending on the which bit is selected or the which data is selected, output will be equal to either to D0 or D1 or D2 or D3. Okay, and this is a truth table. Using this truth table, and this is the expression here, you can actually create a complete logic circuit. Instead of using this ready device, you can actually just create your own logic circuit by using this Boolean expression here. Okay, and this is the circuit for that one. You can implement this. You can try to create this circuit inside the circuitwares, and you can see if the output will match to this existing multiplexer. Okay, and this is how you're gonna read the output in relation to the input when your input is in a digital waveform. Okay, so again we focus on a single clock cycle. So let's say, for example, that we just select this clock cycle here, right? So in this case, let's say the D0 is 1, D1 is 1, D2 is 0, D3 is 0, and then the bit selector is 1 0. So 1 0 means, so in this case the 1 0 means, right, so this is equal to decimal 2, right? So this is decimal 2, so meaning the output will be equal to D2. So this is output here, the output is equal to D2, right? So D2, if you look here, D2 is 0. So D2 is selected here. Okay, so this is how you're going to see the relation between input and then the output. You can consider another one, for example, here, the last one. So D0 is 0, D1 is 0, D2 is 0, and then the D3 is 1. And then this is the data selector bits. So data selector in this case is equal to 1 1. 1 1 is equal to 3, decimal 3, which means the D3 will go to the output. So D3 is equal to 1 here. And this D3 is going to the output, and output is also equal to 1. So this is how the multiplexer functions. Okay, so these are some existing fixed function logic devices. Okay, so these are the existing application or the useful application for the multiplexer. So multiplexer can be used to generate the combination logic functions in SOP form, etc. So I just recommend you to go through these slides and see just the different outputs for the different inputs. And this is a demultiplexer. Demultiplexer is just the reverse of the multiplexer. So if you have the incoming data, so then based on this data selector, you can say where this input will go. Okay, so this is just the output of the multiplexer. Okay. Then we have the parity generators, the checkers. This one is also can be implemented using the very simple logic gates. I will not go into the very details of these circuits, but this is just the existing circuits. You can create them and see how they work, right? So we already covered the parity generator during the last section. We already created the logic circuit for the parity generator, and we already see how it works. So we don't have to repeat it again. You can just refer to our previous lectures. Okay, so this is the end of this lecture. So today we cover the existing different the logic circuits that are created by combining the very simple logic gates, right? So we just created the multiplexers, encoders, decoders, adders by combining the very simple logic gates like it's shown here, right? So in this slide here, for example, you can see this is a parity generator. So this parity generator generates the single parity bit for the input. So this is the input data. For this input data, we can create the parity bit. And as you can see, it's created just using the simple XOR gates, right? So I hope this is useful, because for your final project you have to create some functioning circuit, and of course in that when you do your final year project you have to refer to this lecture notes and specifically to this chapter. Thank you for your attention and see you in the future.